This is part D on the scale factors of similar figures, and this is taken from section 4 of, or worksheet 4 of unit 9. So first, height and perimeter are one-dimensional. It's important to realize that. Area, whether area of the base ratio or surface area, all area is two-dimensional. And volume is three-dimensional. And so when you're looking at ratios of two figures, so we got figure A and figure B, and their height ratios are 3 to 5, that's their one-dimensional ratio. All one-dimensional ratios stay the same, so the perimeter ratio would also be 3 to 5. To go from one-dimensional to two-dimensional ratio, you square those. So we get 3 squared and 5 squared, which is 9 to 25, which would be the same as the surface area ratio. And to get a three-dimensional ratio, you cube the one-dimensional ratio. So it would be 3 cubed to 5 cubed, or 27 to 125. In the second column, we got a 2 to 7 ratio. That's one-dimensional. Perimeter is one-dimensional. So the height's also going to be 2 to 7. That's one-dimensional. The area of the base and the surface area are going to be 2 squared to 7 squared, which is 4 to 49. And the volume ratio is going to be 2 to the third to 7 to the third, which is going to be 8 to 343. In the third column, we have area of base ratio 4 to 9, so the surface area ratio is also going to be 4 to 9, because those are two-dimensional. To go from two-dimensional back to one-dimensional, you take the square root of 4 to the square root of 9, which is going to be 2 to 3. And to find the volume ratio, you cube the one-dimensional ratio. So 2 cubed to 3 cubed, which is 8 to 27. In order to go from two-dimensional to three-dimensional, we need that one-dimensional step. So you go back to one-dimensional and then move forward to 3 dimensions. In the last column, we have the three-dimensional ratio 1 to 8. And you're going to want to go first from three-dimensional back to one-dimensional by taking the cube root of 1 and the cube root of 8, which is 1 to 2. That's your one-dimensional ratio. And then square that to get the two-dimensional. So we get 1 to 4 for our two-dimensional ratios. Alright, in number 1 here, we have two bottles that are mathematically similar. The smaller one is 6 centimeters high and holds 30 I think it should say milliliters. I think we got a misspell there though. Of perfume. The larger one is 9 centimeters high. What's the volume of the larger one? So we have a comparison of heights. Remember, height is a one-dimensional thing, and we have a ratio 6 to 9, small to large, and we can reduce that ratio if I divide by 3. 6 divided by 3 is 2, 9 divided by 3 is 3. So 2 to 3 is my one-dimensional ratio. We want to talk about volume, which is three-dimensional. So if we know our one-dimensional ratio, we can get our three-dimensional ratio by cubing the 2 and the 3, and we get 8 to 27. And we know that the smaller one holds 30 milliliters. Okay, so smaller is 30, and we have x for the larger one. So we're going to take these two right here, the 8 to 27 and the 30 to x, and we know those are equal to each other, so we set up a proportion. 8 over 27 is 30 over x, and cross multiplies. 8x equals 30 times 27, or 8x equals 810. 810 divided by 8 is 101.25, and we're looking at milliliters. That's our volume. Number 2, the two boxes below are similar and both have to be wrapped with decorative paper. If it requires 5 square yards of paper to cover the larger box, calculate the amount of paper needed to cover the smaller box. Notice what's drawn in is they show you the heights. So we're given the heights in the diagram, which is one-dimensional, and we got 24 to 15. We can reduce those, divide them both by 3, we get 8 to 5. So that's our one-dimensional ratio. In the question though, we need to know the amount of paper needed to cover the small box. And if you look at the units for the paper, it's yards squared, which is indicating two-dimensional. This is a surface area type idea. Covering the surface. So this is two-dimensional. And if we have our one-dimensional ratio 8 to 5, we can get our two-dimensional ratio by squaring those. So 8 squared to 5 squared, or 64 to 25. They tell us it takes 5 square yards to cover the larger box. So I'm going to put 5 first because we're going large to small in this problem. And we're looking for how much paper is for the smaller. So here, I'm going to take these two ratios, set up a proportion. 64 over 25 is equal to 5 over x, and cross multiply. So 64x equals 25 times 5, or 64x is 125. X is 125 divided by 64, which is, I'm rounding here, 1.953 square yards. Number 3, the figure to the right is of two shampoo bottles that are mathematically similar, and the cost of the shampoo depends only on the volume of liquid in the bottom bottle. If the small one costs $3, what should the large one cost? Okay, so again in the picture they show you the comparison of heights. Remember, heights is a one-dimensional thing, and we have the small to large ratio 18 to 27. We reduce that ratio dividing by 9 and get 2 to 3. If you read the problem, it's talking about volume and the cost related to volume. Volume is a three-dimensional thing, and so we can get our three-dimensional ratio by cubing the one-dimensional ratio, so 2 cubed to 3 cubed, or 8 to 27. The small bottle costs $3, so 3 goes with the small because that's the price is related to the volume. We don't know what the cost of the larger one should be, so we're going to take those and set up a proportion here. 8 to 27 is 3 to x, and cross multiply. 8x is 3 times 27, or 8x is 81. So x should be 81 divided by 8. And we're rounding a little bit here, so it's $10.13.